So good afternoon, everyone. I'm Norman Wildberger. We're here at the University of New South Wales. And today we're going to be talking about number systems and Stevin's decimals. So the hero of our story today is an interesting fellow called Simon Stevin, who lived from 1548 to 1620 in around the Netherlands, Belgium area. And he was one of the sort of main founders of the decimal number system that we're all very familiar with today. So I want to tell this story which actually connects with important developments in 19th century and 20th century work. So we're going to see later on in some subsequent lectures that in the 19th century people started thinking much more seriously about what's called analysis, or foundations of calculus. And at that point they started realizing that there were some logical difficulties, and that some of the logical difficulties had to do with the nature of number and the nature of the continuum. So there's a kind of an underlying problem with the nature of the continuum. Whatever the continuum is, with our system of real numbers. All right, so this sort of culminated in the 19th century and then into the 20th century, and there's a lot of interesting developments there that we will touch upon. So today's lecture is some kind of introduction or orientation to this general theme. And we're going to have a look, sort of a broad look of the trajectory of things. We're going to talk a little bit about the Greeks and then the Indians, the Arab period, and then to the Europeans, culminating in the work of Stevin and his contemporaries. Okay, so the story really goes back to Euclid, as do many aspects of mathematics, and to the ancient Greeks, where we see that there was as I've talked about in other lectures in this series, there was a big distinction between numbers and geometrical quantities. So numbers and geometrical figures, like line segments, were kept separate. Euclid's arithmetic was concerned with things like line segments and squares and other regions, but he tried to keep a division between the geometrical figures and actual numbers. He was basically following the Pythagorean point of view that basically everything is built up from the numbers 1, 2, 3, and so on. We just build up everything from these numbers and various ratios that we ultimately can make from them. All right, so already there in the ancient Greek times, we've seen that there was a conundrum having to do with irrational numbers. So irrational numbers, such as, well, actually in the Greek time, it was more incommensurable quantities. So they realized that if you take a square and then you take the diagonal of the square, that diagonal is incommensurable with the side. All right, so it's the side, and there's the diagonal. And the way Euclid would have said it is that the diagonal, this ratio or this proportion of the diagonal to the side, was not a proportion between natural numbers, was not a natural number proportion. And so this was sort of the start of irrationalities in mathematics. These days we express that irrationality in a different way. we talk about numbers, and we think about having our number line spread out like that, and we think of identifying points on the line with numbers. We think of them as almost the same things. And what we would say is that what we've established here is that there's some special number called root 2, which represents the length of that diagonal, which is not essentially a rational number. So not a rational number or fraction. In other words, it's not something of the form a over b, where a and b are natural numbers. So this was the beginning of irrationality or incommensurability in mathematics, and it caused the ancient Greeks a lot of worry and concern. It was a conundrum for them because the Pythagoreans liked to think in terms of the harmony of the world as being expressed just in terms of the natural numbers. They thought about astronomy, they thought about music, which we'll talk about a little bit later in this lecture. They thought about a lot of things as just being expressible in terms of natural numbers, and here we have some very fundamental geometrical situation where something's appearing whose length is not in this system. It somehow falls outside some kind of irrational object. Okay, so that's kind of a setup, but at that very early stage, the actual number system that the ancient Greeks had was quite rudimentary. They couldn't do arithmetic at all as efficiently as a year 3 student today can. So that required the next development, which we have to move to the Indian world. So in the Indian period, which roughly is, say, from the year 200 to, say, the year 1200 AD, there are many prominent, important Indian mathematicians. Amongst them are Aryabhata, who lived around 450 or maybe 470. Brahmagupta, lived around 600. Mahavira, that was 9th century, so 1800s. And Bhaskara in around 1100. And amongst many other developments, one thing that they introduced, which is, in my view, one of the most important developments in the history of science, is what we call now the Hindu-Arabic numeral system, the one that we actually use. So the Hindu-Arabic numerical system dates back to this time and to this place. And one of the basic ideas, and this was around the years between 700 and 800. It's not easy to actually specify an exact time when it was created, but it was just a general period. So what are the key features here? Well, the key features are that there are these 9 symbols. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, these weren't exactly the original Indian sort of Sanskrit figures, but they're not so far different from them. And then later on, also crucially, a symbol for nothing, or 0, a special symbol that represents nothing. And of course, the 0 was especially important because it served as a placeholder in this decimal system. So the key features of this system are that it's decimal based. In other words, it's based on powers of 10. That it uses a positional notation. So for example, if we write down 8,704, what that means is that we have 4 ones, 0 tens, 7 hundreds, and 8 thousands. So these symbols here are being used in more than one way. At some level, they represent just the usual numbers from 1 to 9, but they're also being used in a higher sense in in terms of keeping track of the numbers of tens, hundreds, thousands, and so on that are also involved. Earlier civilizations introduced separate words for the bigger numbers, separate symbols. This is a very efficient way that basically we're just using these 10 symbols over and over again in a rather systematic, logical way. So sometimes it's referred to as a ciphered form for the numerals. Of course, the Hindus also dealt with fractional quantities. They also talked about fractions. For example, 3/4 they would write as 3/4, but without the bar. Besides the usual 4 operations, they also went further. So along with the usual 4 operations of addition, multiplication, subtraction, and division, they also took square roots. So for example, a famous formula of Brahmagupta is that if you have a cyclic quadrilateral, that is a quadrilateral whose vertices lie on a circle, like that, that the area of this cyclic quadrilateral can be expressed in terms of the 4 side lengths, A, B, C, and D. If you have a general quadrilateral and you know its 4 side lengths, then you don't know the area because it's flexible. You could change the quadrilateral like this, keeping the lengths the same, but the areas obviously would change. But if you insist that the quadrilateral is inscribed in a circle, that sort of constrains it. And then there's a formula for the area, and it is square root of S minus A, S minus B, S minus C times S minus D, where S is the semi-perimeter, A plus B plus C plus D over 2. And they also had use for square roots in terms of approximations. For example, if they wanted to calculate with pi, they recognized that pi could be approximated. Okay, there was a simple-minded approximation of 3, which is rather crude. But a somewhat better approximation is root 10. They were not afraid to use the square root of 10 as an approximation to pi. What is the square root of 10? It's about 3.162. So it's getting closer to pi, which is 3.1414. Okay, so this was a very huge advance to develop a system for doing arithmetic, okay, where even young people can learn how to do arithmetic in a relatively simple way. So these days, students in primary school, maybe I'll do a little bit more complicated one. How about 9? Okay, if I want to add 123 and 945, I know I start from the right, I add the 1s, and then I add the tens, and then I add the hundreds, I get 10, but I have to carry a 1, and I get 1068. Okay. That works quite well because the notational system is aligned so that the ones, the tens, the hundreds, and so on, they're all written on top of each other. Everything's organized there for you. If you think about doing some kind of arithmetic with Roman numerals, for example, it's much more challenging because there's less structure. And similarly, of course, for multiplication, it's not too hard for young people to learn how to multiply and do the basic operations. Okay, then the story goes to the Arab period. So they have then broadly sort of Arabic-speaking period, which started, of course, with Muhammad, the prophet, whose dates are 570 to 632, establishing Islam and uniting the desert peoples of the Saudi Arabia area. And then a rapid expanse of Islam, so that by 800 we had a sort of well-established large dynasty or empire. And at that time the Arabs became interested in assimilating knowledge from these other civilizations that had come before them. Okay, so there was this sort of a thirst for the knowledge of the ancient Greeks and also the Indians. And so many works were brought into the Arab regions and translated. Works from Greece through Byzantium and other works from India were translated. And then there were a whole range of important Arabic and Persian scholars, mathematicians, who developed them further. So in particular, we had Muhammad al-Khwarizmi, who wrote some important books on arithmetic, and algebra. In fact, the word for algebra comes from one of his books. One of the books had a title with the words al-jabra in the title, and that's where we get our word for algebra. And we get our word for algorithm also from al-Khwarizmi. The term algorithm comes from him. So he took works of Brahmagupta and Diophantus, who was an earlier Greek mathematician, and systematized them, and he and other Arabic mathematicians really organized knowledge and organized mathematical knowledge. In some sense, sort of simplified it. They were very practical people, and they were very conscious of sort of common sense and logical structure. So having good, systematic, and clean arguments. And this was a very important development for European mathematics, because then when the Europeans came along, they really learnt from these three prior civilizations. Right, so in the around the time 1300 to 1500, there was a kind of a rebirth of European mathematics. So in the intervening years, so after the Greeks and the Roman fall, Europe was a bit of a backward place. But around this time, after they recovered from the Black Plague, which devastated Europe in the 1300s, that was a grim time. But after that, there was a sort of a rebirth, and lots of new developments started happening, and Europe became quite a happening place. And so some of the contributions of that are definitely due to these Arabic works that the Europeans imported. The Europeans were very interested in trade. They built lots of ships. They sailed around. They did a lot of business. But in doing so, they also made contact with the Arabs, and they brought back a lot of these Arab translations of earlier Greek and Indian works. So a lot of the ancient Greek works were known to the Europeans through the Arab translations. Sort of went on a hopscotch kind of journey. And this was very exciting. So there were Greek works through Arabic translations. So around 1500, the Europeans started to read Euclid. They started to read Aristotle, Apollonius. And this was a very invigorating time for them because they were very excited by all these fabulous ideas that the ancient Greeks had. Around this time also, 1400s, Gutenberg created the first press. So around this time we actually have books. We have books that are created via printing press. Probably around 1450 or so. And in the space of a few decades there would have been thousands of different books that were circulating around Europe. It's also a very important development. All right, so with this sort of rebirth of European thinking, we also saw the beginnings of modern science. Okay. So modern science has its origins around this time. With the work of Francis Bacon. So we have the beginnings of scientific thought in Europe, where people tried to put some distance between themselves and the religious orthodoxy that had been very strong in Europe up till then. Okay. So there was a bit of religious turmoil around this time. There was something called the Reformation, where the main church, the Roman Church, was challenged by the Protestant churches. And the Protestant churches advocated a somewhat more personal relationship to the Bible, and that you could study the Bible yourself without having to necessarily go through the authority of Rome. So this was a very important development because it sort of freed people's thinking. They thought, okay, maybe there's more flexibility here. Maybe we can think a little bit more widely than we have before. We're not quite as constrained to think exactly in the same way as we had before. That was an important development. But it was also a little bit of one that had some tension in it because the church, the Roman Catholic Church, was still very powerful, and it didn't like people to openly oppose it. And so a lot of the scientists and mathematicians of that day had to be rather careful about positioning themselves with regard to the establishment. And they often did so by orienting what they were doing with a very strong religious basis. So they were doing mathematics, but they presented the mathematics as the language of God, as God's will, as God's plan, and so on. So there was some of that. But nevertheless, some of them did run into trouble. So for example, Galileo, famously, who was also one of the sort of architects of the modern science, was confronted by the church for his perhaps somewhat unpopular views, and he was forced to reconsider his position and officially had to sort of retract some of his positions. All right, but nevertheless, it was kind of an exciting time. And with all these changes socially and with the technology and with the European navies going all around the world, expanding their territories and bringing back all kinds of exotic things from all around the world, it was a very exciting time for the Europeans. And when they got hold of the Greek works, they realized, hey, there's all these really cool things that we can do with mathematics. So there's a kind of a blossoming of mathematics in the 16th and then 17th centuries. So some of the people that were involved on the mathematical side of these things was Regiomontanus, 1436 to 1476, made important contributions to trigonometry. Francois Viette from 1540 to 1603, who was probably the dominant mathematician of his day, a Frenchman. So he made many important contributions, but in particular, he introduced the idea of x. Let x be whatever it was that they were interested in. The idea of letting a letter represent some unknown quantity. So that we all associate this with algebra, and indeed algebra had been around quite some time before that through the Arab work, but the Arab work and subsequent thing was largely word-based. So people expressed things in terms of words. They didn't use letters like X, Y, and Z and then think about formulas just with these variables. That was a very important and kind of crucial innovation that was introduced at this time. And then there's this fellow that we're going to be talking about, Simon Stevin, who lived from 1548 to 1620. And he was born in Bruges, which is in Belgium, sort of Flemish part of the Netherlands at that time. The Netherlands was quite big and powerful country, and that was part of the Netherlands. Even though there was some connection with the Dutch and the Spanish through intermarriage, so for some time the Spanish actually controlled this region. And so the politics was a little bit full of turmoil, and Stevin did get caught up in that a little bit. So he was a number of things. So he was an engineer, a very practical fellow. He was an engineer. He was a practical kind of mathematician. And he was also an inventor. And he was also interested in music. And he's perhaps most famous these days for having written a short book of only 30 or 40 pages. So in 1585, he wrote a little pamphlet called De Tiende, which is a Dutch name for the 10th. And it was translated into French as Le Dixième. So it's worth noting out that at this time, Latin was the language of scholarship in Europe. Latin was not spoken in the streets, but if you were a scholar or a learned person, if you went to some school or university, you would learn Latin. And Latin was the language of communication of scholars. So it was a bit of a departure, in fact, a rather big departure from tradition for him to write in Dutch. He was not the only one to do this. There were a few others. Galileo also wrote in Italian, because he just wanted more common people to be able to access their writings. Descartes wrote in French. But these were the exceptions rather than the rule. Most people would have written in Latin at that time. Okay, so what is De Tiende about? So it's a very important little work which had quite a significant influence on the development of mathematics and, in fact, mathematics education. Basically, what he did was he extended the Hindu-Arabic numerical system beyond even what the Arabs had done. So the basic idea is to systematically use powers of 10 and essentially integer arithmetic even when dealing with fractional quantities. So, for example, well, fractions were well known at this time, in fact, the Hindu-Arabic system was also well known. So that was actually largely due to an earlier mathematician called Fibonacci, who introduced or advocated this Hindu-Arabic numerical system for common use. But by Stevin's time, that would have been well used. But for example, Leonardo of Pisa earlier in 1180 to 1250 would have written fractions like this, what we now call 11 and 5/6. He would have written this as 1/3, 1/2, 11. What we would write as 98 over 100, Fibonacci would have written as 1 over 100, 1 over 50, 1 over 5, 1 over 4, 1 over 2. So people were nervous about fractions, just as they are in primary school. They didn't like fractions. And one way to make fractions a little bit simpler is to not worry about complicated fractions with numerators and denominators, just to worry about having denominators. So have numerators always be 1. These kinds of fractions, in fact, have been around for a long time. They are sometimes called Egyptian fractions because the Egyptians liked these kinds of fractions as well. In fact, that's not hard to imagine why. I mean, if you're starting to think about dividing things up, you have a pie, okay, you're going to try to think about slices of a pie. Well, you're going to divide the pie into 7 pieces, and you can say, all right, this is 1/7 of a pie. And that's now a new unit. But to get 3 of these pizza pieces and say, okay, this is 3/7, that's a little bit more complicated. Okay, so another thing that was around at the time, which made things a little bit more complicated, was also in use was what's called a sexagesimal system, if I'm pronouncing it right. Was a sexagesimal system for fractions.
Sorry, I didn't understand how they wrote 11 and 10.
So when they put them together like this, the implication is you have to add them. So 1/3 plus 1/2 is 5/6. And if you add 1/100th plus 1/50th plus 1/5 plus 1/4 plus 1/2, then you get 98 over 100. So but what made things a little bit more complicated is this sexagesimal system, which is really a throwback from the ancient Babylonian times. Okay, even back before the ancient Greeks. So contemporary with the Egyptians, while they were building the pyramids, there was the Babylonian culture. And the Babylonians introduced a system of dividing things up into 60s. Okay. That's why we have 360 degrees in a circle and not 100. It's because of this ancient Babylonian system that was based on astronomy and working with astronomy. So if you're working with astronomy, you like to cut things up into little pieces, and you don't like to use fractions. So the bigger the number of pieces you have, the easier it is to avoid fractions. So this was still used in for example, with degrees. If you have an angle, maybe this is some angle theta. If you measure this angle, perhaps it's 62 degrees. But if you want to describe it more accurately, then you go to fractions of a degree. Okay, so you may know that, say, you might have 15 minutes. If you divide a degree up, the standard way of dividing a degree up is into 60 minutes. 1 degree equals 60 minutes. And 1 minute is divided up into 60 seconds. So 62 degrees and then 15 minutes and then maybe 43 seconds would be written this way. And that's really equivalent to the fraction 62 plus 15 over 60 plus 43 over 60 squared. So it's a system with base 60, essentially. And of course, that's not unfamiliar to us when we look at time. Time is also hours divided into minutes, divided to seconds. We're dividing by 60. Also coming back from this ancient Babylonian time. So one of Stevin's ideas was forget about base 60. Base 10 is the best base to think about. So how did he write in base 10? So for example, let's say we have a number 3.1416. Okay, so for us, that's an approximation to pi. Stevin would have written it this way. 3, 0 with a circle, 1 with a circle with a 1, 4 with a circle with 2, 4 with a circle 2, 1 with a circle 3, and then 6 with a circle 4. Or he would have written it this way. He would have written 3, 1, 2, 1, 6, and then over the numbers he would have put the exponent, the sort of base 1/10 exponent, a 0, a 1, a 2, a 3, a 4. So he's indicating the exponent, the power of 1/10. Of course, what this really is for us, this is 3 plus 1/10 plus 4 100ths, or 10 squared, plus 1 over 10 cubed, plus 6 over 10 to the 4. And so he's recording these exponents here with these circles either beside or above the numerals. A little while later, Napier, actually someone else, but Napier popularized the idea of a decimal place. So Napier, around 1617, introduced our present notation to dispense with these things and explain where things are centered with this decimal point. 3.1416. Once you know where the decimal point is, then by convention, everything to the right has the proper exponent, just as in the Hindu-Arabic system, everything to the left is ones, tens, hundreds, and so on. Now it's 1/10ths, 100ths, 1,000ths, and so on. So how did Stevin advocate arithmetic? Basically, he said that with this system, we can do arithmetic just as we do for natural numbers, just as we do for integers. So he was interested in simplifying arithmetic for the common people. Instead of this complicated system with fractions that's very tough to remember and figure out, what you do is something like this. So here is a calculation that actually appears in Stevin. So 0, 1, 2, 3. So here's his way of representing what we would call the ones column, the 1/10ths, the 100ths, the 1,000ths. Okay, but he didn't have this. He just had these numbers in circles. And then he wrote 27, 8, 4, 7, 37, 6, 7, 5, 875, 7, 8, 2. So for him, he lumped the integer part all together. The standard natural number is just in the zeros column. So this means 27. This means 37. This means 875. And then to add these, he would say, well, you just add them as if they were integers. You start on the left and go down, and when you carry, well, you carry. So there's a 7 plus 5 plus 2, that's 14. You carry the 1, and then you get 5, 7, and 8. That's a 0. Carry a 2. 10, 23, 16, and 21. And then you get 94. But he also applied this methodology with having these exponents in circles to polynomials, to Vieta's polynomials with variables. So also, for example, well, we would write x to the 4th plus 3x squared minus 7x. He wrote as 1, 3, minus 7, and he put a 1 over here, a 2 over here, a 4 over here. There's no actual x, but you can see the coefficients, 1, 3, and minus 7, and you can see the powers of x above here because these circles represent powers to him.
So is that how we went from that to powers, from Stevin's?
Yeah, so there's a very close link between Stevin's decimal arithmetic and then ultimately Newton's approach to polynomials and power series. Yes. And he also was interested in square roots, so he used 1/2 and 1/3 for square roots and cube roots. Well, what about repeating decimals? What about regular fractions? Like we all know that if we have a fraction like 1/3, that if you write that as a decimal, you get 0.333, and it keeps on going, repeating. Well, Stevin knew about that. So he knew that fractions correspond to repeating decimals. He also knew that if you took a square root, some algorithm that was well known from the ancient days, Indians knew a square root of algorithm. If you perform a square root algorithm, also you get a string of decimals that keep on going. So we see the beginnings of what are these days called real numbers. So real numbers are close to appearing in Stevin's work. And some people assert that, in fact, Stevin might be thought of as sort of the father of real numbers. But I think that's saying a little bit too much. Stevin was a very practical person. He was an engineer. And he wasn't particularly interested in decimals that keep on going forever and ever and ever. He was interested in realizing that in practice you truncate the decimals and you want to do arithmetic with finite decimals. In fact, his method of doing arithmetic requires that you have finite decimals because you have to start on the left just as you do for integer arithmetic, whether you're adding or multiplying or subtracting. If you have infinite decimals, it requires a lot more thinking about how you're going to set up a theory of arithmetical operations for infinite decimals. Okay, I'd like to mention a few other things that Stevin was just involved with very briefly. So he was also involved in music. And he was interested in a fundamental problem that occurs in music, which has to do with the nature of the scale. Okay? So the ancient Greeks were very interested in music. They realized that if you had a scale like do, re, mi, fa, so, C, D, E, F, G, A, B, C. So there's your standard scale. Do, re, mi, fa, sol, la, ti, do. Okay? So the ancient Greeks realized that if you go from C to G, that's what's called a perfect fifth. Do, so. That interval is a perfect fifth. And the frequencies of the proportion between the frequencies was 3 to 2 for a perfect fifth. And for a perfect fourth, like this one, the frequency was 4 to 3. That's like do, re, mi, fa, do, fa. That's a perfect fourth. Do, fa. If old acquaintance. Okay. So if you have a 3 to 2 ratio and you have a 4 to 3 ratio, then the combined ratio is 3 to 2 times 4 to 3, which is 4 to 2, or 2, which is a representation of the fact that an octave is doubling a frequency. If you go from do, do, that's an octave. You double the frequency. This was all a very beautiful system that had been worked out by the Pythagoreans, but unfortunately there was a serious flaw arithmetically in it. The flaw is that if you take this fifth and you repeat the fifth, you go out to the D, you get this what's called a circle of fifths, very important in jazz. So C, G, D, and then there's an A, and then there's an E, and then there's a B, and then there's an F sharp, and then there's a C sharp, and then there's a G sharp, or A flat, and then there's an E flat, and then there's a B flat, and then there's an F, and then there's a C. You get back to C. So C, G, D, A, E. And the problem is that if this was all going to work correctly, then if you have 3 to 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so 3 to 2 over to the 12th power ought to be the same as the number of octaves that you're going. You're going one octave here, another octave here, that's 2, another octave here, that's 3, 4, 5, 6, 7. So it should be equal to 2 to the 7. If everything worked out. But it doesn't work out because these are not equal. This is 128, and this is 129 point something or other. Okay, what is 129.746. And because of this mathematical difficulty, if you're a musician, you find it very hard to tune your instrument consistently for lots of different scales. If you tune your instrument really well for one scale, it doesn't work in another scale. And so Stevin sort of wrestled with this, and he was one of the original advocates of something called the WellTempered Scale. which basically said, let's forget about the 3-to-2 ratio and just make sure that each one of these leaps is a 12th root of this. So what you do is you cheat a little bit. Everything gets a little bit adjusted, but then there's a uniformity between the various scales. And Johann Sebastian Bach, the famous composer, liked this system so much that he made a very famous piece of music, the Well-Tempered Clavier, which is well known to all people who study piano, to advocate the use of this. And finally, Stevin was also responsible for the following remarkable observation, that if you have two weights and you drop them, and there are different weights, and you drop them a certain distance, the heavier one does not fall faster. They drop at the same time. Okay, so this one's lighter, this one's heavier, but if they're the same shape, let's make them the same shape. Okay, same air resistance, then they will fall, they will hit the ground at the same time. This observation is usually credited to Galileo, who also made the observation, but in fact Stevin had made it earlier. It's a very important observation. So Stevin really set the stage for a lot of future developments, in particular Newton's work on power series, very much built on Stevin's idea of reducing everything to powers of something. A very important development that also sort of opens the door to this important question of what's really going on with this real number system.